Welcome to Spring LIB.
This is the answer to Chapter 31, problem number 18 from the Smith Organic Chemistry textbook. And this problem is extremely similar to Chapter 31, problem number 16. And so we're told that Lexan, which is a polymer, can also be prepared by acid-catalyzed reaction of diphenyl carbonate with bisphenol A, and we're asked to draw a stepwise mechanism. So again, just as with the previous problem, number 16, as I said, this is going to be just addition to a carbonyl, formation of a tetrahedral intermediate, and then a leaving group being kicked out to reform the carbonyl. And so I do want to begin by drawing your attention to these abbreviations. So rather than redraw these large pieces of the molecule that don't participate in this reaction, I'm going to abbreviate as R the majority of I'm going to abbreviate as R the majority of this bisphenol A, and I'm going to abbreviate as pH the two phenyl rings on the diphenyl carbonyl compound. And so to begin, we're told that this is acid catalyzed. And so the carbonyl oxygen from this diphenyl carbonyl is going to, or diphenyl carbonate, pardon me, is going to grab a proton from the acid and become protonated. And so again, if we think back to the carboxylic acid derivatives chapter, the purpose of doing this is to put a positive charge on the oxygen. This makes the carbonyl carbon much more electrophilic and therefore much more susceptible to nucleophilic attack. And in this instance, the nucleophile it's going to attack is one of the hydroxide groups on this bisphenol A. So as I said, I'm choosing to abbreviate the majority of this molecule as R. What I've drawn here that I just underlined in black, that HOR, is what I've drawn up here with just the OH where this squiggly line is. So I hope everybody follows that. It's much more time and space efficient to omit the majority of this molecule that's not going to do anything in this reaction. And so a lone pair on that phenol is going to attack the carbonyl carbon. These electrons will kick up to the carbonyl oxygen. And so that is going to be the formation of our tetrahedral intermediate. So tetrahedral intermediate formed, positive charge on that oxygen that was the nucleophile in that reaction, in that step of this mechanism, rather. And so now the conjugate base of our starting acid. So if this initial proton here, so we can imagine that came from the dissolution of HA into H plus and A minus. And so the conjugate base would be the A minus, the anion. And so this conjugate base can grab that proton. Those electrons will revert to that oxygen. And so now we are here. And so from here, what will happen next is that one of these phenoxide groups will next be protonated by another molecule of acid. So there are lone pairs on these oxygens. One of them can grab a proton. So this oxygen now has a positive charge on it and 3 bonds. And so, of course, what this sets the stage for in this type of reaction is for that group to leave. And so it can just leave as phenol. And so when that happens, we'll be here. Let me actually go ahead and show the bond here, so that'll make drawing this next step just a little bit easier. So OH, and of course carbocation there. And so what can happen now is we can invoke another conjugate base of our starting acid to come and grab this proton, and when it does so, the electrons of this bond will revert down and add to the carbon-oxygen bond, and so we've reformed our double bond. All right, so there we are. And so at this point, I'm actually going to go ahead and draw out exactly what this would look like. So at this point, what we have is this molecule. So remember, our R group actually looks like this. And we have another potential oxygen nucleophile there. And we have another ester group here that can be replaced the same way that the first one was here. So another potential nucleophile here, and another ester group with the potential to be hydrolyzed and trans-esterified away there. And so basically, we just repeat this process for all the other ester bonds that there are using these oxygen nucleophiles. And when we do that, and I will just write repeatedly. So when we do that repeatedly, what we end up with is our desired polymer. And so we can see this would continue on indefinitely, um, alternating between one monomer and the next. And so, again, this is really just a series of carbonyl reactions. So the mechanism, the answer to this problem, the mechanism that you need comes from the earlier chapter on carboxylic acid derivatives and their reactions. And again, just remember, I've abbreviated some things in this problem. I would encourage you to do that whenever possible. Probably not on a test if it can be avoided, but otherwise, it's always best to abbreviate rather than write things over and over and over again that aren't participating in the reaction at hand. And so that's the answer to chapter 31, problem number 18.